In our second course, CS198.2x, we decided to take a huge step back to look at some of the big problems in the blockchain space. Having studied Bitcoin and cryptocurrencies in CS198.1x, the previous course, now we take a step back and look at the fundamentals issues. And in the first lecture, we talked about achieving trust without trust, and more particularly about distributed systems and consensus. At its core, consensus is a social issue. How do we reach a majority opinion, or how do we achieve a general agreement? Consensus is trivial if I'm the only one agreeing with myself. But the moment when I try to come to consensus with some other peers, then it gets a bit more tricky. The formal study of distributed consensus started really with the study of digital avionics, wherein they decided to put computers in very adversarial environments, such as on an airplane. And the formal study of distributed systems really started with the famous author Leslie Lamport. And today, consensus can be found in jet planes, spacecraft, distributed lock servers in a cloud compute environment, and also, of course, the topic of this course, blockchains. At their core, distributed systems can be seen as a collection of nodes and messages, and we can look at them on a graph where nodes are the actual nodes, the computers, the processes themselves, and edges are the messages that have been passed. Some of the properties of distributed systems are that there are concurrent components, there's no global clock, and most importantly, there's the potential of failure of individual components. So the question is, how do we achieve a reliable system from unreliable parts? We looked at some of the categories of properties, including safety and liveness properties of distributed systems, and also defined correctness in terms of validity, agreement, and termination. We then looked at one of the more famous theorems in distributed systems, and that is the CAP theorem, where you can only have two of the three: consistency, availability, and partition tolerance. We then ran through a quick demo proof of how we can only have two of the three, and also observed that the CAP theorem isn't really a black or white trade-off, but actually on a spectrum. And especially in the case of blockchains, the trade-off is generally more between CNP and ANP. We then looked at one of the more famous papers in distributed systems, which is the Byzantine generals problem, in which we have generals surrounding a city separated geographically, and they have to agree on whether to attack or retreat. They all have to agree on doing the same thing, and they can only communicate with each other through messengers. The messengers can get lost, and also there may or may not be a traitor among them. And it turns out, to reach agreement, there is no solution for greater than 1/3 traitors. The Byzantine generals problem teaches us to classify faults in two ways, being fail-stop faults, in which nodes just simply crash, and also Byzantine faults, nodes that can lie to each other or send corrupted messages. And the parallels between the Byzantine generals problem and that of public blockchains are pretty apparent. Then we looked at some of the more traditional consensus algorithms, where nodes explicitly vote. One of the earliest was Paxos, which told the story of the Paxon Parliament, in which proposers, acceptors, and learners all tried to agree on which decrees to pass. And the parallels between the Paxon Parliament and the distributed systems are quite similar. And there's a pretty clear correspondence between the database systems that we know and the Paxon Parliament. Paxos is used in practice in many of these companies listed on screen, such as Google, WANDisco, IBM, for distributed lock servers or of the like. And other distributed consensus algorithms of the same class include Raft and PBFT. We then looked at some of the newer classes of consensus mechanisms, in which nodes consume resources. And this is the class of consensus mechanism that proof of work falls into. And also proof of stake, proof of activity, proof of burn, proof of space, and proof of elapsed time. We then looked into more detail into proof of stake, where instead of miners, like in proof of work, we have validators. Then looked at some flavors of proof of stake algorithms, including chain-based proof of stake and Byzantine fault-tolerant proof of stake, and also some implementations. We then looked at federated consensus, in which we can form quorum slices. And the demo here is that if I'm trying to agree with my friends on where to get lunch, I don't have to trust anyone other than my immediate close friends. And if anyone else tries to join, then we can use the intersection of our friend groups to make sure that we all agree on where to get lunch. So following the lecture on consensus mechanisms, we took a deep dive into proof of stake and also the crypto economics that secures it. Breaking down crypto economics, there's the cryptography side, which aims to secure the past, and also the economic side, which aims to secure the future. In terms of cryptography, we have cryptographic hash functions. We give us awesome properties in terms of the immutability of the blockchain, and also give us digital signatures. And for economics, we have primitives such as tokens and privileges. We also looked at the carrot and stick model, as well as the concept of security margins, uncoordinated choice models, and normal form games. Then looking back at proof of stake, we realized that there's problems such as nothing at stake, which can be solved using slashing. There's also the long-range attack and stake grinding. In the next lecture, we looked at enterprise blockchains. In the past, there was a rise in interest in private blockchains or permission ledgers. These blockchains are not open and not trustless and lack the incentive structures like in the previous lecture where we talked about crypto economics. In analyzing enterprise blockchains, it was useful to step back and classify blockchains in general. Specifically, blockchains are databases at their core. And databases, we can see them as centralized databases and also distributed databases. A subclass of distributed databases are distributed ledgers, and distributed ledgers, which specifically use the structure of blocks chained together, are called blockchains. We then classified blockchains in terms of their access control. Namely, we have public blockchains like Bitcoin and Ethereum, and permission ledgers, such as consortium blockchains and private blockchains. We saw that there's various tech companies that are involved in the blockchain space, and also some varying perspectives on the whole blockchain movement. We clarified some misconceptions and also some things to look for when evaluating enterprise blockchain platforms. We then introduced a very fundamental observation that we carry over in the next three sections, and that is the scalability trilemma, in which you can't really have all three of security, decentralization, and scalability. There are some implicit trade-offs that have to happen. For enterprise blockchain platforms, we looked at Ethereum, Hyperledger, Corda, Chain, Ripple, Rootstock, Quorum, and Cosmos and Tendermint. We then did a quick survey of the use cases and industries in which blockchains are currently being deployed, including auto and mobility, big banks and financial institutions, travel and tourism, digital identity, healthcare, insurance, the Internet of Things, supply chains, real estate, and foreign aid. And then after all of those, we looked at some enterprise blockchain use case generalizations, in which we saw that in many use cases, blockchains are viable, but not really necessary. We also looked at the term efficiency when applied to blockchain and how it may be misleading. In general, blockchains are good at solving coordination failures, horizontal integration, and, of course, pure decentralization. And it turns out there are advantages of centralized solutions. So the big question is, why is using a blockchain better than using a centralized database? And that's something for you to decide when you're evaluating your own use cases. We then did a quick survey of the ICO scene, looked at some of the drawbacks, some statistics, AML, KYC, and also some perspectives on enterprise blockchains. And these spanned states and global as well. And these perspectives are both good and bad. Having seen all these use cases for blockchain, we then looked at the next lecture, which is called Cryptocurrencies for the Masses, Scaling Blockchain. And this lecture looked at the fundamental problem of scaling blockchains, namely at the current problems that we're facing today, as well as dreams of how we can scale these blockchains in order to power the use cases that we looked at in the last lecture. Fundamentally, scaling, we're trying to increase the TPS, so we can either increase the volume of transactions or decrease block time. And we also looked at the size of the blockchain. Blockchains may be scalable in that they're super fast and can support lots of TPS, but when it comes down to it, storing the blockchain is also a very big problem as well. We then looked back at the scalability trilemma, having covered the decentralized portion on the bottom left in the previous lecture on enterprise blockchains and how there's varying categories of blockchains based on their access controls. Now we look at the bottom right section of the triangle, which is on scalability. In terms of scaling techniques, there's the usual vertical, horizontal, and diagonal scaling. And also, blockchain specifically, we have layer 1 and layer 2 scaling. And that refers to whether scaling solutions belong on the blockchain or off the blockchain, off-chain. A naive solution might be to increase the size of blocks, thereby increasing the throughput. The problem here is that because the time to broadcast blocks stays fixed, then we have some nasty side effects, which include the blockchain increasing in size too fast, and also naturally occurring forks. A way we could possibly fix this is perhaps using Ghost. We then looked at increasing the block size. Some pros and cons, of course. And also of decreasing transaction size, in which some implementations might be segregated witness, like in Bitcoin, where we move the signatures from within transactions out to a separate structure called the segregated witness, and of course, some pros and cons. We then looked at ZK snarks and how we could use recursive snarks also for scalability. All these previous scalability techniques were all on-chain scalability techniques, or layer 1 solutions. And the observation now is that we've run out of variables to play with. We looked at the size of blocks, size of transactions, and also block creation rate. But that's pretty much all we can do on-chain. So we need to look at something else. So let's just not use the blockchain. We looked back at the fundamental problem of Bitcoin transactions and how long their delays are. The idea of payment channels is to bypass the blockchain and instead create a private payment channel where Alice and Bob can pay each other off-chain. The way this would be implemented would be Alice and Bob would open a private balance sheet on the blockchain, so that's one transaction, conduct as many transactions as they want off-chain, and then settle the final balance back onto the blockchain. And then there's the idea of the Lightning Network, creating a network of payment channels. In terms of scalability, Lightning Network can help us achieve up to tens of thousands of transactions per second. But there are centralization concerns in terms of the Lightning Network. Sharding is a horizontal scaling solution that is traditionally used in databases, and we can now use them on blockchains. And the idea behind sharding blockchains is that now we have multiple parallel blockchains. Of course, with all this complexity, there are concerns in terms of the varying node categories and also single shard takeovers and cross-shard communications. There's also the idea of sidechains, in which blockchains plug into each other like hub and spoke. There's a particular sidechain scalability solution called Plasma. And blockchain at Berkeley's Fourth State Labs are implementing Plasma on Cosmos. And Cosmos allows us to scale diagonally, looking at both the speed that Tendermint allows us, as well as the interoperability of blockchains in the Cosmos network. In summary, we reconsidered the role of consensus mechanisms in scalability, and also categorized all of our scaling solutions that we looked at. Having looked at the problem of scalability, another big problem in blockchain is that of privacy. Firstly, we resolve the question of whether anonymity is really only good for cryptocurrencies in terms of buying drugs. The answer is no. We pose some hypothetical situations in which anonymity is necessary for a properly functioning currency, as well as some security concerns. We looked at the fundamental architecture of public blockchains in which everyone stores everything and saw that blockchains are mostly pseudonymous. All of our transactions are stored on the blockchain for everyone to see, and there are methods of linking or de-anonymization in which people can link your pseudonym to your actual real-world identity. And even if a technology might be anonymous or pseudonymous, there are some human factors that we have to consider. We noticed a slight paradox when trying to achieve anonymity and security on the blockchain, and saw that it all ties back to the scalability trilemma, in which we're sacrificing some decentralization or some scalability for the purpose of security. We then looked at the process of linking, where we can use a transaction graph, some clustering, as well as some heuristics, including merging of transaction outputs and also the existence of change addresses, in order to identify organizations or individuals. We then looked at some more advanced techniques, such as taint analysis. We saw that one way to achieve anonymity was mixing. We made some formal definitions of anonymity sets and the goals of mixing, as well as some desirable properties, such as being trustless and plausibly deniable. We sought to increase the size of our anonymity sets to make it harder to link our pseudonyms to our real-world identities. Some types of mixers include centralized mixers, altcoin exchange mixing, decentralized mixing protocols, and privacy-focused altcoins. And we looked at all of those. We also looked at decentralized mixing protocols, including CoinJoin, CoinShuffle, JoinMarket, and CoinParty. We then looked at some privacy-focused altcoins, including Dash with its masternode network, Monero, which uses crypto-note technology for ring signatures to have untraceability, and also unlinkability through one-time addresses. We also took a look at Zcash, which uses ZK snarks, as well as a zero-knowledge security layer. There are also some advanced anonymity solutions, one of them being Mimblewimble, which aim to simplify the Bitcoin protocol to make it much more secure. And in simplifying Bitcoin, we see once again we're making a compromise in terms of the scalability trilemma. And now we've made it all the way to the end. This is the last lecture in the Blockchain Fundamentals program, in which we talk about a blockchain-powered future.